Hello, welcome to my CS520 presentation 3. My name is Zhu. This is my email address. Today I'm going to improve the inductive case of topic 1, which has been listed over here. First of all, let me state what the base case is. So basically today I wanted to prove that this equation is correct. The left hand side equals the right hand side. The base case is simply just n equals to 1. So what happens to n equals to 1? Basically, when n equals to 1, the left-hand side turns to something like this. It actually equals to 1 square, and is equals to 1. And the right-hand side turns to something like this. The denominator, it's 1 times 2 times 3, and the denominator is 6, and is also equals to 1. So basically we prove that the left hand side and the right hand side are all equal to 1. And we prove the base case is correct. But proving that the base case is correct is not enough. We have to prove that for every n, this equation is correct. We have to introduce the inductive hypothesis to prove for every sk, it implies to sk plus 1. So basically, for every term k, it's the next term, k plus 1, is also applicable to this equation. So we assume that this equation is exactly the same with the equation that we are proving today. We simply just change the letter n to letter k. But k is something that we introduced here. So this is the inductive hypothesis, but here we have to prove the inductive hypothesis. Basically, we wanted to prove that for the k plus 1's term, this equation is also correct. So basically, we substituted k with k plus 1 here, and for every k we substituted with k plus 1. If we can prove this equation is correct, we can say that the equation proving is successful. So how I generated this equation? I'm going to improve here with some writing. So here I wanted to prove the left hand side of this equation equals to right hand side of the equation. How I did that? So the left hand side basically equals to first I copy it here, k plus 1, I equals to 1, and I square. And this actually equals to the first case terms sum. Okay. Plus the last term, which is the k plus 1 square. And it equals to this term, it's what we assumed in the previous slide, the inductive assumption. So the first part equals to this assumption and plus k plus 1 square. We just copy it. And I wanted to add them up together. So I basically multiply 6 to the denominator of the second term, and it also equals, and here I factor out k plus 1, and what left behind I just copy it. What I left behind here, it's 6 plus k plus 1. And here I want to open the parentheses for the second part of the denominator. It's also 6 k plus 1. Okay, now here I want to open the parentheses here. That's 2k squared plus k and plus 6k plus 6. Okay, this is k. and it is equals to denominator is also 6. First term is k plus 1, and the second term changes to plus 7k and plus 6. And then I wanted to factor the second term of the denominator. Here I factor out a k plus 2 and it times a k, 2k plus 3. And then I just modify it to something that I feel comfortable. Basically, the first term changes to k plus 1 and times 2k plus 1 plus 1, which is exactly what the right hand side looks like. So here I prove that the left hand side equals the right hand side. Basically, till now we proved that the equation is applicable to every k or every n. For this presentation, I don't have any references. Hopefully I have proved it correctly and illustrated clearly and understandable. Thanks for watching.